These are general statement. I don't have to repeat it, right? Mankind has been always interested in symmetric things, all right? And they gave special status to the symmetric objects. The next question is, what is symmetry, right? You can have a geometrical picture, right? You don't have to look at that thing, right? Take any object, a triangle, right? You can think of what are the transformations which leave that triangle exactly the same as before doing that transformation, all right? And in the case of an equilateral triangle, you can rotate it with respect to the centroid 120 degree, it will come back to the same thing, right? You can think of reflection about the, what is that, lump of wood, and that also is a symmetry operation. But one thing you should note, not all transformations need not be a symmetry transformation. There are, some of them are symmetry transformations, some of them are not, all right? Now, this is a geometric picture, right? Now, you know that when you think about quantum mechanics, you are studying microscopic system, right? You cannot think of going inside a hydrogen atom and see what are the symmetry operations like this, right? So you should quantify what exactly a symmetry transformation is, right? There are two kinds of all right. One is, this is as far as a geometrical object is concerned. Next thing you can do is, in physics you have all kinds of equations, right, governing the dynamics of the system. You could think of symmetries of the equations of motion also, all right. Now, the next question is, what are the transformations we can think of in physics, right? There are again two classes of transformation you can think of. One is geometrical, all right, or you call it as kinematical or dynamical. What is that? Actually, all transformation, it could be continuous or discrete also, all right. For example, rotation is a continuous transformation, right? And the rotation can leave the system invariant, then you call it as a symmetry transformation, right? Examples are space translation. What do I mean by space translation? You look at the system and next you look at the system in a different coordinate system which is displaced with respect to that original coordinate system, right? See, is there any change, right? And if you don't see any change, the system is translationally invariant. Similarly, rotation, all right. So there are other, if you go to relativity, there is another transformation which is Lorentz transformation, right? In fact, if you want to think, you can think of Lorentz transformation is kind of a rotation in 4-dimensional space also, but you need not. But that is also the another important transformation we are considering, all right? Because all these transformations are continuous, right? You can rotate by 0.5 degree, 0.51 degree and that kind of thing, all right? But there are other transformations, discrete, okay, these transformations may be symmetric or may not be symmetric, right? There are discrete transformations like reflection, right? There is no question of 0.5 reflection, 0.6 reflection, right? There is a reflection or no reflection, right? Similarly, time reversal transformation, they are all discrete transformations, and the system could be invariant under, symmetric under these discrete transformations also. These are all dynamical transformation, but in physics, there are other, you consider the transformation of system in different space, all right. Best example is isospin transformation, all right. I don't want to go into the details. So there are internal transformation and the system could be invariant under that transformation also. The best example is in strong interaction or in nuclear physics. really there is no difference between proton and neutron, all right. So it is called isospin symmetry. Where gauge transformation, we will get into that in somewhat detail later. A gauge transformation could be global or local. There are discrete internal symmetry, internal transformation also. Example is a charge conjugation. Charge conjugation is you consider a system, transform system is you replace all the charges of the particle to change sign, all right. Actually, what is the outcome, all right? It's a well-known result. Henry Poincaré showed that these symmetry transformations forms a group, right? That means you make one transformation, another transformation. Combined transformation also belong to the same set. So you know what is meant by a group, right? They obey the axioms of group theory. And particularly in the context of quantum physics, due to Wigner, what is that? Group theory has become a part of physics, all right. As itself, it was standing as a mathematical thing, but group theory has become part of the physics. Now I think Nambudiri sir mentioned about it, but he was telling it in a different context, right? Symmetries not only have aesthetic value, but it simplifies the complicated description of a physical system. For example, think of a physical system which is rotationally invariant. I mean, the best example is, you think of Earth, Sun system, right? They are at a distance r. So when you think of a rotation, if you keep the distance r fixed, right, there is no potential energy change, right? Then you say that the system is invariant under rotation, because the potential depends only on the distance between the particles, right? And you don't have to do any dynamics, or you need not know what actually is the interaction between these two particles. You can immediately conclude angular momentum is conserved because the system is invariant under rotation. So without doing any complicated analysis, so that kind of thing happens, right? So this is the famous theorem, right? Noether's theorem, associated with any continuous symmetry transformation. There is a conserved current. Actually, conservation current is well known in electrodynamics, right? What does it tell you, right? That is that equation. d rho by, you take a small volume, all right? You calculate d rho by dt at a point. Since you cannot create or destroy charge, the change in the charge density should come either from outside, current going into the point or going away. So that is that equation, del dot J, all right. So that is in a way it contains conservation theorem in the sense that continuity equation tells if you calculate this quantity Q, which is I'm sorry, it is not J0 or rho, all right. This has to be rho. So I was using 4-dimensional. In a pointer, read it as rho, okay. In fact, this is as far as electrodynamics is concerned. You can think of a system which is translationally invariant, rotationally invariant, right? Corresponding to all these things, there will be current conservation, and from that current conservation you can construct similar to charges, but it's called charges in quotation, right? Charges can be energy, momentum, 3-component, or angular momentum, okay. So I will tell you that energy of the system is conserved provided the system is invariant under time translation, all right. Similarly, linear momentum is concerned if the system is invariant under space translation, all kinds of things, okay. electric charge, you can always associate a symmetry transformation associated with the conserved current, all right, conserved quantity. This is an interesting thing, right? Are the laws of nature always symmetric, right? Then the next question is, if it's not symmetric, what is the thing which causes that breaking, right? If it is always perfectly symmetric, it is boring, if you want to say, right? If it is entire system is completely asymmetric, that is also boring. So it may be both are there. No, it is both are there. Okay. System there are symmetry as well as non-symmetry situation. Now, if you want to break a symmetry, for example, you take a hydrogen atom, right? You know that it is rotationally invariant. Okay, there is no difference if you look at a rotated hydrogen atom without rotation, a particular angle and another angle, axis also, right? But if you put a magnetic field, that rotational symmetry is broken, all right? Then there is only axial symmetry, rotation about the magnetic field, right? So if you want to break a symmetry as in this situation, you can apply magnetic field along one direction, right? So symmetry is broken. In fact, that is a cause for the Siemens splitting. In fact, you can think of isospin symmetry and breaking, right? May lead to proton mass different. In fact, what I want to concentrate is on spontaneous symmetry breaking. These are explicit symmetry breaking, right? If you have a Hamiltonian, okay, I forgot to say that thing. How do you quantify a particular system is symmetric or not, right? I can say it, I cannot, there is no point in saying in words, right? If you think of in physics, the dynamics of the system is decided by the Hamiltonian. So you take the point of view that if the Hamiltonian is invariant under what kind of transformation you are considering, you say that the system is invariant. So you should check for whether the Hamiltonian is symmetric or not under that particular transformation, right? So in this example, explicit symmetry breaking, originally the system is invariant under some operation, but you added terms which break that symmetry, all right? There's another way you can implement symmetry breaking, that's what is spontaneous symmetry breaking, all right? So what exactly is spontaneous symmetry breaking? For that, we should always distinguish between the symmetry of the dynamics, all right? For example, let me give you a very simple example. Take Laplace equation, right? Del square phi equal to 0. We know that del square is del dot gradient, right? Any scalar product is invariant under rotation. So del square is invariant under rotation. Does it mean that all the solutions you obtain are spherically symmetric? You know that Laplace equation, depending on the boundary condition, you get a non-symmetric solution also, right? So an equation symmetric doesn't mean that the solution you are going to get has to obey the same symmetry, all right? It's not surprising. So spontaneous symmetry breaking is exactly that thing, right? You have a symmetric system, for example, the Hamiltonian is symmetric, but that solution you are writing down do not respect that symmetry, all right? We'll make it more quantitative when we discuss quantum description, all right? There is one thing there, you know, if you do explicit symmetry breaking, for example, take hydrogen atom, apply magnetic field, you may say that the effect of the magnetic field is very small, you can do perturbative calculation. But spontaneous effect of spontaneous symmetry breaking is non-perturbative, all right? There are various examples. Phase transition can be considered as spontaneous symmetry breaking, ferromagnetism, superconductivity, formation of crystal lattice. I think what you should think is, if you take in solid state condensed matter, your original Hamiltonian is translationally invariant. Why the hell, the system choose a crystal structure, right? So that kind of the original translational invariance is completely lost, and you have crystal lattice is an example of spontaneous symmetry breaking of the translational invariance, if you want. Similarly, ferromagnetism, rotational symmetry is spontaneously, right? So this is we need to consider both aspects, right? It is not that you should study symmetry alone. Broken symmetries are also important, and in fact we will give you the use of spontaneous symmetry breaking later, probably depending on the time. The point is, studies of broken symmetry has equal status as symmetry itself, right? So both of them existed peacefully. There was no problem, right? Actually, it follows principle of mutual coexistence, right? In fact, if you look at some of the important milestone in broken symmetries, right? Earlier, people thought parity is a good symmetry. Parity means, in simple terms, it is if you look at a system and its mirror image, right? It exactly looks the same. So people thought, all physical systems should obey that symmetry. There is no difference. But it is found that system interacting weak interaction, do not respect that symmetry. So parity is not a symmetry transformation for weak interaction Hamiltonian, all right, or Lagrangian, whatever it is. And in fact, it is verified experimentally, all right. Actually, it is proposed by C.N. Yang and T.D. Lee, experimentally verified later. There is another violation which is called CP violation. C is charge conjugation, P parity, all right, in beta decay. That also got Nobel Prize, right? So not bad. Broken symmetries are considered seriously. Actually, this spontaneous symmetry breaking is known in condensed matter physics for a long time, all right. What Nambu pointed out is you could implement this kind of thing in relativistic quantum field theory also. I don't want to go into details. Superconductor phase is also a kind of due to spontaneous symmetry breaking. Actually, Nobel Prize in 2008 got Nambu, these people, they received Nobel Prize, all right. These are the people. Only thing I could ask is why this person got half and other two 1/4. All right, that is a good question, all right. All right, let's see this. What exactly I mean by a state of the system do not have a symmetry, but the Hamiltonian of the system has symmetry. All right. For that, I'll remind you, because all of us are at least one course in quantum mechanics. You know that state of a system is described by vectors in some linear vector space. I denote it by ket psi. Dynamical variables are represented by operators, right? And the important thing is there is actually a transformation in real space, right? How do I implement that transformation in the Hilbert space or the linear vector space corresponding to every transformation? For example, if you think of rotation, right? There is a physical rotation, but that physical rotation is implemented in that vector space by some unitary operator. Okay. Unitary operator means U dagger is 1. Alright. So there are two things. One is state of the system psi. Operators corresponding to observables, linear momentum, angular momentum, or whatever it is. And there are transformations between states, alright, U, denoted by unitary operator. To see why spontaneous symmetry breaking is not a trivial thing, let's take a simple example, right? No algebra, I will tell you what it is exactly, right? You think of a lattice where at each lattice there is a spin, right? And you know that the spin can be either up or down. So each lattice is up or down. And let's assume the ground state is at all the sides of the lattice it is spin up, right? And you can think of rotation of that state by some angle theta. And you denote the transformed state by theta. So let's rotate the system about y-axis by an angle theta. A vacuum state in field theory is state with minimum energy. So in this situation, vacuum state is all the spins are up every lattice state, and you rotate it with respect to y axis by an angle theta. I call 0 prime and denote it by theta. Alright, one can construct what u is, don't worry about that thing, alright. The important thing is you look at the transformed state theta, take the scalar product with the initial ground state, you get this expression. It's interesting because you know that cos theta is less than 1, right? Oh, of course there is a theta equal to 0 is 1. So if you take n goes to n infinity, this scalar product goes to 0. So what happens is there is a ground state 0 I call. 0 means all the spins are in a particular direction, right? Then you rotate it, I call it as theta, ket theta. That vector is orthogonal to ground state, alright. It tells you that you cannot obtain the particle state with the different theta cannot be unitarily connected. You cannot get one from the other by a unitary transformation, right? So that the another way of stating is there is an infinite number of degenerate vacua, if you want. For one cannot be obtained from the other by a unitary transformation, alright. But what is important to note is to get the spontaneous symmetry breaking, what need not go to thermodynamic limit means a large system or n goes to infinity, okay. Alright. Under a particular transformation, your state of the system will be transformed to psi goes to psi prime, and corresponding to that transformation, there is a unitary operator. O goes to O prime operator. Both, see, in quantum mechanics, you have to consider both, right? You should worry about transformation of the state as well as the observables, right? So this is the transformation, right? And you say that system is invariant under this particular operation provided this quantity remains the same, okay. Since u is unitary, u dagger is equal to 1, you can always write u as exponential of I alpha q, alpha real, and q is Hermitian, okay. And you call this q as the generator for the infinitesimal transformation, alright. My point is, if it's a space translation along x-axis, q will be px, linear moment in the x direction. So they are the generators of a space translation along x-axis. Similarly, if you think of rotation, angular momentum is the generator for the rotation, alright. Anyway, there are prescription to calculate what Q is. Let's skip that thing. Now this is the point, what exactly spontaneous symmetry breaking is, right? The question is the following, all right? You have a vacuum state, right? Then you ask, what happened to that vacuum state when you do the transformation, right? So transformation can be written as, this way, right? What are the things involved in the transformation operator U? How much you transform alpha, and this is the generator for that transformation. In the case of linear momentum, it will be px, py, pz or whatever it is, right? All right. Now the question is the following. If you rotate the vacuum state, again I repeat, vacuum state is the state with minimum energy, all right? There are two possibilities, right? If Q acting on the vacuum is 0, is it all right? Gorilla. U acting on 0 will give you 0 itself. So you say that vacuum is invariant under rotation. What is the condition for that thing? Q acting on that vacuum state should give you 0 vector, all right? But what happens if Q acting on 0 is non-zero? Then U acting on the vacuum state will not give you vacuum, all right? So the vacuum is not invariant, then we have Nambu-Goldstone. That's realization is called Nambu-Goldstone realization. Then there is a theorem coming in, right? Whenever you break a symmetry, some continuous symmetry spontaneously, there are massless particles existing in the picture, and okay, they may be useful or may not be useful. That is a different issue. Examples of Goldstone bosons are, you can think of chiral symmetry, left-right symmetry. If it is spontaneously broken, you get a scalar particle. In fact, it is really, in particle physics, it is pion is approximately that thing. Condensed matter, it is phonons, ferromagnetism, spin waves and other things, okay. This is the thing I want to give little more importance, right? Now let's go to what happens to spontaneous symmetry breaking in gauge theory, all right? You know what is gauge invariance, right? Probably you are familiar in electrodynamics. You have an electric field and magnetic field, right? If you want, you can express electric and magnetic field in terms of scalar potentials and vector potentials. What is that? B equal to B equal to del cross A is one example. That automatically tells you that del dot B is 0. Right? There is another equation for electric field. Electric field is equal to minus gradient of phi minus dA by dt. All right. That will automatically tell you Faraday's law. So Faraday's law and non-existence of magnetic monopole is automatic if you use scalar and vector potential, right? That's the thing. Now there is a question, if you think of 4 Maxwell's equation, may not be 4 if you make the component, 2 of them, del dot B equal to 0 and the thing associated with Faraday's law, right? Del cross E equal to minus dB by dt. That has to be obeyed by all systems. It has no dependence on source, all right? So it's not considered as equations of motion. They are called constrained equation, all right? These two. There is a difference, all right? And in that sense, this is a point of view, not mine, right? Can you, the gauge transformation, can you call it as a symmetry transformation? Of course, the system has to be gauge invariant, but that whether that transformation, can you call it as a symmetry transformation? There is point of view that you need not consider it as a symmetry transformation. So this is a famous professor, Xia Gang. He is a student of Princeton, that famous, anyway, Witten, right? He was originally, should be particle, okay, he maybe worked in string theory, but അതിലൊരു മെച്ചമൊന്നുമില്ല എന്ന് കണ്ടിട്ടാണ് തോന്നുന്നു പിന്നെ he became a famous condensed matter physicist, right? So he is presently a condensed matter physics. So his argument is gauge invariance is not actually a symmetry transformation, right? It reflect, you have excess degrees of freedom existing in the description, all right? So it's related to the constrained problem also. So you cannot take a thing which is not a symmetry cannot be spontaneously broken, all right? But in fact there is a theorem, right? This is that Elitzur's theorem. Local gauge symmetry can never be spontaneously broken, all right? ഏകദേശം ആയിട്ടുണ്ടാവും അല്ലേ? നന്നായി. The point about, but that one can think of spontaneous symmetry breaking in gauge theories. I am not talking about spontaneous symmetry breaking of the gauge symmetry. The point is you have a Lagrangian or Hamiltonian, whatever it is, which is gauge invariant, right? Then you break the symmetry spontaneously. You know that when you break the symmetry spontaneously, there are Goldstone bosons, which is unwanted. So what happens in gauge theory is this Goldstone boson, it was massless originally. It coupled with gauge boson. Okay, gauge theory means there are gauge bosons. In electrodynamics, it is the photon, right? And gauge invariance means photon is massless originally. So, but in the case of weak interaction and other thing, originally gauge bosons are massless, but due to spontaneous symmetry breaking, this Goldstone boson combined with this massless gauge boson and obtain a massive gauge boson, which is called W plus W minus a set bosons. Okay. In fact, spontaneous symmetry breaking is a good way to generate mass. Only thing is there is it will introduce massless particle which is unphysical sometime. You should find a way to eliminate it, right? Gauge, yeah, I think I have it here. Massless gauge bosons it will give you. There is a good thing about gauge theory is it is a renormalizable theory in the sense that there are ways to eliminate infinities from the problem or renormalization, right? All right. So in the case of spontaneous symmetry breaking in gauge theories, you can generate mass. But if you look at fundamental theory of weak interaction, right, SU2, whatever it is, you generate masses for the quark, or masses you generate it by spontaneous symmetry breaking, all right.